Swayam Prabha. Digital India. Educated India.
Good morning to you. In the last few lectures, about 6 or 7 lectures so far, we were focusing on deriving the governing equations, describing the flow and heat transfer. Of course, we have done that in a Cartesian coordinate framework as well as a coordinate free framework based on applying the Reynolds transport theorem. And finally, so we were looking at approximations to two-dimensional incompressible flows to Navier-Stokes equations. One is casting that into form of stream function vorticity equations, which we have derived, and if you apply that to a typical problem, which is for a external boundary layer flow. Okay, so for that we can use some scaling arguments, do some order of magnitude analysis, and then conclusively show that certain terms can be dropped out, provided that you are dealing with sufficiently high Reynolds number flows. Okay, so under that approximation we have derived what are called as the boundary layer equations. Okay, so let us summarize the boundary layer equations which we derived in the last class. Okay, so let us write it in a dimensional form, not the non-dimensional form. So finally, the continuity equation stays as it is. Okay, so the boundary layer equations, what we are writing here is for 2D incompressible and for steady state flows. Okay, steady flow. Okay, so of course, and this is also, we are assuming they are laminar. Okay, that is another important assumption. So something I have to tell you about this. When we derive the Navier-Stokes equation, we don't really derive one set of equation for laminar flows and another for turbulent flows. The Navier-Stokes equations are valid for all kinds of flows. Okay, so the problem is in solving those equations numerically. So most of the times, if you are applying the same set of equations for turbulent flow, and turbulence has a lot of features, you have to resolve all kinds of scales in turbulence, length and time scales, and therefore numerically it may not be possible to do that kind of resolution. So then what we do in order to model the turbulent equations, turbulent flows, we construct what are called as Reynolds averaged Navier-Stokes equations. Okay, so we average the equations that we have, and we can do different kinds of averaging. Of course, for steady state it doesn't matter, we have ensemble average. For unsteady problems we can do time averaging, and when we do this averaging we are trying to get information only on the mean properties of the flow, such as mean velocities, mean pressures and mean density. We are not interested in all the microscopic turbulent fluctuations and turbulent quantities. Okay, so therefore we are going to when we apply these kind of equations to model turbulent flows, I think when Professor Kolar comes, I think he will discuss how we average the corresponding equations and then we get the Reynolds averaged Navier-Stokes. Structurally everything will look similar. Only apart from the laminar stresses, you will also end up with turbulent stress term. Okay, and the problem is how do we close this particular turbulent stress. Okay, so that is all the different turbulence models are about. Okay, so there are different there are many books written on turbulence modeling, so many hundreds and hundreds of papers published on that. So this is a very important issue where most of the practical flows are turbulent. Okay, as such if you solve the Navier-Stokes equations as it is there is no problem, but most of the times you cannot resolve all the scales, and therefore you have to approximately model what are called as averaged quantities, and that's where the Rance equations come. So far we have not discussed those things. I am just looking at plain Navier-Stokes equations and approximations. So you can say safely that this is mostly applied to laminar solutions. Okay, so when we solve this, the resulting solutions are all for laminar flow. Okay, for turbulent flow again the characteristics become a little bit different, and therefore we have to solve the Rance equations, and most of the times you don't have analytical solutions. Okay, you have to solve them numerically, but a few extreme cases have analytical solutions which we can do. Okay, so this is the continuity equation. This is your momentum, only your x momentum stays, your y momentum tells you that your dp by dy is approximately 0, and finally your energy equation. Okay, so what should be the viscous dissipation term here? Okay, by rho but what is the rho Cp, right? I am dividing by rho Cp everywhere, so this is k by rho Cp, which is alpha, mu by rho Cp times du dy the whole square. Okay, so this is the only term which is staying there. Alright. Okay, so these are the boundary layer equations finally. So all of you agree, and you know why only this term stays, right? Okay, so if not, you please go back and revise. So now in order to solve these equations, what do? We need definitely some boundary conditions, right? These are partial differential equations. So can you tell me what are the boundary conditions that we can apply? Say we take the case of our flat plate, the same yesterday we have a momentum boundary layer delta thickness, thermal boundary layer delta T, and the wall is maintained at a constant temperature, and you have a flow u infinity T infinity. Okay. So now you have to tell me what are the boundary conditions which we can apply for first the momentum and next the energy. Okay, so at y equal to 0, so how many boundary conditions we need in the x direction? For example, the momentum, as far as the velocity is concerned along the x direction, how many boundary conditions? 3. Why? Okay, so if you are too much bothered about okay, I am just asking for velocity. Okay, so 2 along the x. Why? So why do we need 2? And how about in the y?
We only need 4. We only need 4. 2 plus 2 or 3.
2 plus 2, what is this combination?
2 in x direction and 2 in y direction.
Why 2 in x direction? What is the order? What is the order of the PD in x direction? First order. What is the order in y direction? Second order. okay. So how many boundary conditions does a PDE need? Equal to number of, what is the order of the PDE, right? So therefore for along the y direction how many we need to give? 2, okay. So one we are saying at y equal to 0, u is equal to 0. So this is what? No slip boundary condition, okay. So this is the biggest contribution to Prandtl, okay, who has invented the boundary layer theory. He discovered that the fluid velocity should be exactly identical to the solid wall velocity, okay. Now also when you complete saying no slip and there is no vertical velocity or there is no transpiration through the wall, okay, the vertical velocity also has to be 0. So and what is the other boundary condition along y we can give? Y, okay, let us say y going to infinity, okay. So your u infinity, okay, and so therefore you have two boundary conditions with respect to u, and now what is the remaining boundary condition we need to give? One in along x, okay. So we will say at x equal to 0 u should be u infinity, okay. So similarly for the temperature, the temperature also requires two boundary conditions along y, one boundary condition along x, okay. So what is the boundary condition at y equal to 0? Either this, or if I apply a uniform heat flux instead of uniform wall temperature, if I say my q wall is constant, so then it should be minus k dt by dy at y equal to 0 should be equal to 0. Why? It should, what happens if it is 0? Huh? It's adiabatic boundary condition, okay. So therefore this is the condition at y equal to 0. How about at y going to infinity? T should be equal to T infinity, and x is equal to 0 at T should be T infinity, okay. So these are the required boundary conditions to solve the boundary layer equations, alright. So now we will first see the solution for the flat plate flow. So this is also called the Blasius solution. I think most of you are familiar with Blasius solution, okay. So this is anyway a flow problem you must have done in your fluid mechanics as well as in the heat transfer. Anyway, for the convective heat transfer we have to revisit the flow problem before going to the heat transfer. So I am going to go through the solution, okay, in probably in a slightly different way from how it was done before. So for the flat plate case, what are the approximations we can make, okay. Still you should understand that this is a considerably complicated set of equations, even if you write it for a boundary layer, and of course we can transform this into a form which we can solve, okay, and we are going to do that. But before we go to a complicated case where we have a pressure gradient, okay, so now we are going to first apply that to a very simple geometry, the flat plate, okay. So for this case what kind of approximation that you can make? Can you see some approximation further to this? Pressure gradient is 0, okay. So therefore since your free stream velocity is constant, okay, so this term can be knocked out that we have seen yesterday, and also right now we could retain the viscous dissipation term and solve, okay, but that is a slightly complicated way of solving it, and we are not going to do now. If time permits, towards the end of this course I will take up this particular case, okay. So what it means, even if you have an adiabatic boundary, suppose you put minus k dt dy y equal to 0 is 0 and you have this viscous dissipation, you will find a temperature profile, okay. So this is something which we will be taking up when we have, if we have time, okay. Otherwise for this particular case when is the viscous dissipation important? As we said, when you have the ratio of your Eckert number by Reynolds number which is kind of very high, okay. So when that can be possible? When your flow speed is high, because your Eckert number is directly function of the flow velocity, or your Reynolds number is very small, that is extremely viscous flows or very high speed flows, okay. So in those two cases you have to consider the viscous dissipation, okay. So in the other cases, the moderate velocity regimes, okay, you can safely neglect this term also, okay. So the resulting equations now look slightly much more simplified, and this is what we are going to solve for the Blasius solution. So before going into the solution, just to give you a brief history how this was originally proposed. So first it was Prandtl who pointed out in 1904, okay, Ludwig Prandtl. He was a very famous German physicist, mathematician and aerodynamist who was actually credited with the invention of boundary layer, the concept of boundary layer. And in 1904 he says that the boundary layer equations for flat plate, okay, can be transformed into a ordinary differential equation, okay. So in those days they didn't have very sophisticated computers, and therefore whenever anybody was looking at set of PDEs that looked like, they could not solve it, because numerical methods were not that popular. There was no computer at that time, okay. So they could not find a direct closed form solution to the PDE, but Prandtl proposed that if we can convert the PDE to a ODE, okay, so an ODE is always solvable, even numerically you can do it by hand also, okay. So therefore he proposed that the boundary layer equations can be transformed to an ordinary differential equation, and this transformation is through what is called similarity variable. So this is the it's a great concept that he introduces, that all the time we don't have to go for a numerical solution. If you are clever enough to see some kind of relationship between the flow velocity, non-dimensional flow velocity, and the property and the, for example, the coordinate that it is dependent on, if you cast them in a correct form, that you can transform the PDE directly into a ODE, okay. So this is called as a similarity solution, and in fact it was a student, Blasius, okay, in 1908 who did it actually, who did this similarity solution for the flat plate, which we are going to do. So what we are going to do next is we are going to identically trace what Blasius exactly did it, exactly in the way that he solved it, okay. So this he got the solution for the flat plate velocity profiles, okay. So he was his student, and later on I think it was Polhausen in the year 1921 who extended the Blasius solution for velocity profile to solve the energy equation, okay. Okay, so it took almost a decade to solve the energy equation from the original Blasius solution, and then in 1930 was Falkner and Scan. There were two people, Falkner and Scan, who actually extended the similarity method of solving the PDEs to flows with pressure gradient also, okay. So far we are neglecting this particular term here, but they have extended for a generalized set of flows, flows including pressure gradient, without pressure gradient. So all of them they constructed a similarity solution, which we are also going to see, okay. So these are general family of problems, okay. So therefore you can see that it had a considerably long history, and in fact in the first in this course, when we are talking about external flows, we will be doing all of this, okay, starting from the Blasius solution till Faulkner and scan, and probably an extension of this to different boundary conditions. Okay, so all these are basically closed form solutions which you can do, but of course the resulting ODE cannot be solved analytically. Blasius himself struggled with that. We will be using some elegant numerical techniques to do that. Okay, so now we will start with the Blasius solution. Okay, now what Blasius thought. Now if you look at the velocity profiles, okay, so you can draw the velocity profile something like this here. If you go a little bit downstream, so if I were to calculate the gradient of velocity at the wall, du by dy, okay, so what will happen to this gradient as I go downstream? Will it increase or will it decrease? It will decrease, right? Decrease. Why? What is that? It's always 0. Always at the wall it is 0, but why the gradient should decrease?
The boundary layer thickness keeps on increasing.
Yeah, the boundary layer thickness keeps on increasing, and you have more flow which is entraining from outside. Okay, so therefore the profile becomes more gradual and gradual as you go down. So initially you have a very sharp gradient. At x is equal to 0, the gradient will be infinite. Okay, so you don't have any profile which is developed. Okay, slowly your profile develops and it becomes more gradual, and it has to satisfy continuity also, right, downstream. So therefore what he has observed, if you can find a variable, okay, so a non-dimensional form of the velocity which we can say u by u infinity, because we can see the order of magnitude of u is of the order of u infinity, right. So if we say u by u infinity, this should be some function of some variables. Now you can see the variables which you are dependent on. It is a function of two variables, one is your x and the other is your y. Okay, now when you look at delta, you can also see delta is a function of x. Clearly the boundary layer thickness is a function of x. So therefore now also we saw that y scales with delta very well. Y is of the order of magnitude of delta. So therefore if we combine these two variables as a non-dimensional group, so he says that if we can write this as some function of y over delta, which in turn delta is a function of x. Okay, so this is a non-dimensional group, and if we can find this function, so this should directly explain the dependence of y on this single variable rather than on variables y and x, right. So if you say y by delta is some variable eta which we call as similarity variable, okay, so now your u by u infinity is just a function of eta directly, and once you use the similarity variable, you don't have to solve this in terms of x and y, you can just directly solve in terms of eta. Okay, that will help you in reducing the PDE to an ODE. So that was his basic observation. Okay, now how he obtained the basically the relationship between eta, y and delta. So now we should know how delta is a function of x. Okay, one, directly you can use simple scaling arguments like what Bejan does. Look at the inertia and this terms balance, and then you can directly get the functionality of delta. Okay, the other long way that I am going to do is helpful, because anyway we don't have to derive the same set of equations again. Okay, so and that's what I am going to do now. So what I am going to do is I am starting with the x momentum equations, and I am going to integrate it along y from the wall surface all the way till the boundary layer thickness delta. Okay. So if you integrate it out, so directly you reach to this particular form. and what I am going to do now is a little bit jugglery here to eliminate in terms of V and construct that in terms of U. So how do I do that? I want to from the continuity, okay. So your continuity says that your du by dx, this is equal to minus dv by dy, okay. So I can write for V, I can integrate this and I can say this is minus integral 0 to delta du by dx into, so integrated 0 to delta over dy, and now we can so this is your kinematic viscosity, so we can substitute for, so I can substitute into that, okay. So what I am going to do a little bit more, I am going to integrate by parts. This particular term I can write it as so d by, I can write this as d by dy uv dy integral 0 to delta, right, minus 0 to delta u dv by dy dy, right, d, what is that? I think this is right, okay. Which one? Okay, so I am integrating by parts, okay. If I do that, this I can directly write it as uv between the limits 0 and delta, okay. So this will give me, of course at 0 u and v are 0, at delta u is equal to u infinity, so I can say that this is u infinity times v at delta, okay. So minus this particular term here, and of course from continuity I know dv by dy can be written in terms of du by dx, okay. So therefore this can be further written as minus u infinity, so v at delta is this right here, this is my v at delta, right. So I have integrated it from 0 to delta, and at 0 v is anyway 0, so v at delta will be this, so I can substitute for v of delta from here, so this will be minus u infinity times 0 to delta du dx dy, okay. Again dv by dy as minus du by dx, so this will be plus integral 0 to delta u du by dx dy, okay. So this is how my second term, so now you can see I have eliminated v completely, I have written everything in terms of u, okay. Is that clear? Which part? Integration by part, okay. So basically I have integrated by part here, okay, and then the first part, if you integrate it you will end up with between the limits 0 and delta, at 0 the velocities are 0, at delta u is nothing but u infinity multiplied by v at delta, okay. Now from the continuity equation, when you integrate it between 0 and delta, your v of delta can be expressed like this, so I am just substituting for this directly here, and dv by dy is nothing but minus du by dx, okay. So I am just using continuity to plug in, okay. So this is the resulting equation, so if I substitute for this term and then write the complete equation, so you have to tell me how the resulting equation should look like, okay. So already you have u du by dx, there is another u du by dx, okay. So that will be 2 times integral 0 to delta u du by dx dy, and then you have minus u infinity 0 to delta du by dx dy, that should be equal to mu dou u by dou y at, now this has to be integrated from 0 to, so this is the limits I am applying. Okay, this is nothing but, okay, you can call this, put this as equation number 1, and please store it in your mind somewhere that we have derived this equation, because I am not going to do it again when we do the integral method. Okay, so this is nothing but the momentum integral equation. So that is slightly cast in another form. You can say this is du square by 2 dx, and 2 cancel, so you can write du square dy minus u infinity. So that is slightly cast in a different form, but anyway that is basically coming from this particular equation.
This has done change that v into u in terms of.
Yes, this is your momentum integral. Your momentum integral is written in only in terms of u. Your entire equation is in terms of u. There is no v coming there. Okay. Okay, and of course your, you know your momentum integral, right? What is your momentum integral? Theta. How is it denoted? U by u infinity integral 1 minus u by u infinity dy 0 to, this is the definition of momentum integral. Okay, or people call it as momentum thickness sometimes. Okay, so we can, you can do this as a nice exercise. You can combine these two terms, bring it to this form, and then write in terms of d theta by dx. Okay, so that is another way of casting this equation. Okay, so anyway, so that we are not interested in solving for the momentum integral right now. What we are going to do, we have already assumed that my u by u infinity is a function of my g, which is function of y by delta. This is nothing but my similarity variable eta. Okay, so I am going to plug in this particular solution, form of solution which Blasius has assumed, into this particular momentum integral. So why I am going to do all this is, finally I have to solve for delta. Okay, so first if you calculate your du by dx from here, how will you calculate du by dx? So that is basically u infinity times okay, so you should go back and revise all your differentiation rules. Huh? Okay, g prime, and then minus y by delta square into d delta by dx. Okay, so how you got it? You can say that this is some function of eta, right? And so your du by dx is nothing but u infinity times dg by dx. Okay, so this is nothing but dg u infinity times dg by d eta into d eta by dx, and now dg by d eta is nothing but your g prime. Okay, and d eta by dx, so this eta is nothing but y by delta. Okay, so then you get minus u by y by delta square into d delta by dx. Okay, so you please go back and revise your differentiation rules. Okay, so once you get this, now the next term that we need here, what is the other term? Du by dy. Okay, so what will be du by dy here? Du by dy is much easier, u infinity into g prime by delta. Okay, so but delta is a function of x, so you don't have to differentiate it. Okay, so now you substitute for this du dx and du dy. Okay, and you can group all the terms together, which I am not going to do step by step. I will only show the equation after it is grouped. Okay, so if you substitute into 1, and you group all the terms. I am just going to write the final form. You get something like a minus b into delta d delta by dx is equal to nu by u infinity times c. Now this a, b and c are constants, where a is equal to 0 to 1 g prime y by delta into d y by delta. So what I am doing is this integral dy, wherever I am writing this as dy by delta into delta. Okay, so therefore the integral limits become 0 to 1. Okay, so you can check that. It's a nice exercise. You can, it doesn't take too much of time. You are just rewriting everything in terms of y by delta, grouping the terms together, and b is 2 times 0 to 1 g prime y by delta into d y by delta, and your c, can you now guess and tell me what c should be? This you should be able to tell. 0 to 1. Why? It's already integrated and the limits have to be applied. What is du by dy? U infinity g bar by delta. Okay, so actually when you put that, all of this u infinity can be cancelled off. So you have nu times g bar. Now g prime between the limits delta minus delta 0 divided by, you have another delta, and that delta also will cancel off. So finally c will come out to be g prime of 1 minus g prime of 0. Okay, so this, because you are transforming all your y with respect to y by delta. Okay, so wherever you are applying limit delta, that becomes 1. Alright, so this is your ODE. Can you tell me what is the solution for this? How do we solve this ODE? Separation. Okay, so what will be the solution for delta? Okay, so I can write this as d delta square by 2 by dx is equal to c by a minus b into, so I can separate it as you said, nu by u infinity into dx. Alright, so if I integrate it from x is equal to 0 to some position x, okay, so I can use a dummy variable here, and I can say I can integrate from 0, x is equal to 0 to some position where you are interested to calculate the boundary layer thickness. Okay, so this will give my delta is equal to, so 2 times square root of 2c by a minus b into square root of mu x by u infinity. Okay, so therefore you can see clearly that we have arrived at a relationship between delta and x. Okay, so your delta therefore is a function of x through this particular relationship, and therefore if you say your y by delta eta is equal to y by delta, so that will become y times square root of u infinity by mu x. Therefore this is my similarity variable. Okay, this is my similarity variable, which goes like this. So this similarity variable, now you can see, is constructed as a function of both x and y. Okay, so now if I do this way, what it means, my u by u infinity is going to be a function of only eta anymore, so not on x and y respectively. Alright, and this is the similarity variable. Now the same result you can get by a very just one step process, scaling process, which you can do it yourself. Okay, and now what I am going to do is introduce a similarity transformation. Now still I have not converted the PD into ODE, and still I do not know whether this similarity variable is correct. This is just what Blasius has assumed. So what is the check that this variable is correct? So when we substitute that variable into the PDE, it should get converted into an ODE. That is the proof that you have a similarity solution, otherwise the similarity variable that you guessed is wrong, correct. Okay, so let us go and check that. So I am going to see, now I have to introduce a function so such that I can make the continuity equation redundant. I don't want to solve this, so what kind of function should I introduce? Stream function. Okay, so stream function naturally satisfies the continuity. Okay, so therefore I will introduce a stream function such that your u is equal to d psi by dy and v is equal to minus d psi by dx. Okay, now if I take this particular and integrate it along y, so I get 0 to y u dy, and already I know my u by u infinity is nothing but g of eta or g of y by delta. So I can just substitute in terms of delta here, this is 0 to y, okay, u d y by delta which is d eta into delta, right, or I can just say dy by d eta into okay, so I can directly transform it this way. Okay, so dy by d eta you know, so now we have constructed a relationship for eta which is your y square root of u infinity by nu x. Okay, so you can calculate what dy by d eta is. What is dy by d eta here? Square root of nu x by, okay, so that I can substitute into this, and I can write this in terms of g. Okay, so this will be 0 to eta, so y I am transforming to eta, and u is equal to u infinity which I can take out into g of eta into d eta into you have square root of nu x by u infinity. So this is nothing but your square root of u infinity nu x times 0 to eta g of eta d eta. Okay, so this is your psi, and now I am going to introduce another function, okay, function which is says that this integral is nothing but a function of eta. So you can use dummy variables here, and you are integrating from 0 to eta, so the resulting function which is a function of eta I am denoting it by f of eta. So therefore your psi is equal to square root of u infinity nu x f of eta. Okay, so this is the relationship between the stream function which I am going to introduce and your similarity variable eta. Okay, I hope all of you got it. It is just a very simple substitution and writing in terms of eta. Any questions on this? Okay, so now we have done this, so just couple of more minutes and I am going to write down the velocities and derivatives, everything in terms of the similarity variable eta. Okay, any questions? Is it clear? Okay, so all I am doing is I am transforming from y to eta. Okay, so I already know the relationship between eta and y, so I substitute for dy by d eta, and I already know u is a function of eta this way, so I substitute and finally get the relationship between psi and eta. So now first your u, okay, your u by u infinity already we know it is a function of g of eta, okay, and your g of eta is nothing but, if you look at this particular definition, is nothing but df by d eta, right, because integral of g of eta is nothing but f eta. Okay, so therefore g of eta has to be what? Df by d eta, that's right. Now similarly my v velocity, is nothing but minus d psi by dx. So now you have to tell me. So you have psi as a function of eta, so this we have to differentiate with respect to x. Okay, so you have to do this and tell me. I think with that we'll stop today. Okay, so if I group these terms together, so finally I should be getting v by u infinity. This should be equal to 1 by 2 square root of nu by u infinity x into, so this term right here I can write this as eta into df by d eta, okay, minus f. Okay, so you can check for yourself this particular, it's a little bit of jugglery, so you can cast this in terms of eta and you can check whether this particular form comes out. Okay, so this is you have to play a little bit around there. Okay, so with that we will stop here. Tomorrow we will plug. So why we are doing all this, we are first getting an expression for similarity. This is your stream function as a function of the similarity variable, and then in your boundary layer equations you have your velocities, your derivatives, all of them have to be now cast in terms of the similarity variable. And how we are doing that, because we know velocity is a function of psi and psi is a function of similarity variable. Okay, so we have to use that, put them in the PDE, and finally you will be ending up with a nice ordinary differential equation. Okay, so I suggest all of you, whenever we do these kind of derivations, especially in the beginning where you are not used to so many differentials, you please go back and pay some, spend some half an hour, 45 minutes checking all these equations, and I think slowly you will get accustomed to this, and after that you will become faster. Okay.